Topic 3A, Review of Linear Algebra. This lecture is not intended to be a comprehensive treatise of linear algebra, but more just to review some of the main topics that we will be using in this computational methods class, and really no more than that. And the expectation is that almost everything in this lecture is review that you would have seen before somewhere. Before jumping into matrices, I want to just take a small system of algebraic equations and solve them by hand with algebraic substitution, and then draw the parallel when we solve that in matrix form and we put those equations into matrices. Then we'll step through some matrix terminology, some special matrices like the identity matrix, zero matrix. We'll talk about matrix math, addition, subtraction, multiplication, pre-division, post-division, that sort of thing. Okay, on to solving systems of equations. So not matrices yet. We start with a system of linear equations, and we see these on the left. They are linear, they don't contain any square roots or cosines or anything like that. And very often in science and engineering, we'll have a huge set of these equations. And some very efficient algorithms have been developed for solving those. And first, we would usually cast those into matrix form. To better understand what happens when we deal with matrices, we first have to look at what happens with just our standard linear algebraic equations. So we start here, and let's say we want to solve this for all of our values of x. X's in this case are our unknown values. The a's in these equations are our constants. There should be numbers there. And the b's on the right-hand side are also constants, and they usually describe some kind of excitation if you're solving a problem in physics. So for this example, rather than solve a huge set of equations, let's just take 3. So our goal here is to solve for the x's. The methodical approach to this would be step 1, solve the first equation for x1. Then what we'll do is we'll take this expression for x1 and we will substitute that into equations 2 and 3. That will eliminate x1 from equations 2 and 3. So when we do that, we end up with a revised set of equations. We have our original equation, but we have 2 new equations that no longer contain x1, and the information from that has been substituted into these other parameters. That's why on the a's and the b's we see that superscript. That indicates that those parameters have changed once the information from equation 1 has been substituted into them. At this point, we will repeat the process, but now with the next equation. We will solve equation 2 for x2, and we end up with this equation. We will then take this expression for x2 and plug it into equation 3 to eliminate x2 from the third equation. After we do that, we end up here. And by the way, every time we substituted x1 or x2 into the following equations, we've been calling that forward substitution. And we finally end up in this form. And notice on the left-hand side, this sort of looks like an upside-down triangle or something. And this is going to come up again later. If we were to put this into matrix form, these terms would end up in the upper half of the matrix, making a triangle. We would call that an upper triangular matrix. But we use forward substitution to end up in this form. And as you'll see, we are just about ready to solve this. We've done most of the work. The very last equation in that set of 3 equations, we can easily solve for x3. And now we have all numbers in our b's and our a's, and we get a numeric value for x3. At this point, we'll take our value for x3, bring that back to the second equation, and we can use that to solve for x2. We call that backward substitution. This step is very quick and simple. And then finally, once we have values, numerical values for x2 and x3, we can back substitute those into our equation 1 and solve for x1. So this was very fast and simple. The forward substitution, the first part of this, there was more work there. But once we got to that final form of 3 equations, the backward substitution made it very fast to solve. And that theme will come up over and over in this course. So that's solving a system of equations by hand. Now let's talk about what happens with matrices. We'll go back to this system of linear algebraic equations, and we have n of them. And n can be any number. We could have a huge set of equations and a huge set of unknowns. We can always take this huge set of equations and write them in matrix form. So all of these coefficients that likely had numerical values, we lump into a big square matrix. Our unknowns end up in a column vector, and any constants on the right-hand side of the equal sign, our b's, also end up in a column vector. So the only two things that are column vectors here are the unknown and these constants on the right-hand side that are probably some sort of excitation. Now this is a little bit more convenient to write, but still not that convenient because there's a whole lot of numbers stuffed into these. So what we'll do is we'll have a shorthand notation. This big matrix full of these A coefficients we'll just call A, and we can put them in square brackets to remind ourselves this is a matrix. Our column vector of x's we'll just write as an x with square brackets. Our column vector of b we'll write this way. Now, for a lot of things, I use this notation a lot while we're starting out, but I really don't like this notation with the square brackets because I really want to use the square brackets like I'm going to use parentheses or braces, and it eliminates one way of sectioning off parts of equations. So I actually tend to prefer this notation where we use bold letters to represent matrices. Usually I use capital letters for big square or rectangular matrices. Column and row vectors, I tend to use lowercase letters. But I use bold. It makes them look big and fat, like there's a bunch of numbers behind them. But more importantly, this leaves me the option to use square brackets to section off parts of equations. If we look at a matrix, we can look at the numbers formed into rows. And this top row is called row 1, the second row, row 2, and so on. And notice that the rows start with row 1, not row 0. This is why in MATLAB thinks everything is a matrix, and that's why arrays in MATLAB start at 1 and not 0 like in other programming languages, because MATLAB is accessing matrices, whereas other languages are accessing arrays. Likewise, we can look at the columns, and they progress from left to right. Column 1, 2, 3, 4, and so on. It's also very common to talk about the diagonals of a matrix. And usually when we just say the diagonal, we're referring to the center diagonal down a matrix. But if we were to number these, we would call this the 0 diagonal. And as we progress to the upper right, we have our diagonal 1, diagonal 2, diagonal 3, and so on if it was larger. And below that, we have our diagonal -1, -2, -3, and so on. And sometimes these diagonal elements are called the pivot elements. And we won't talk too much about pivoting in this class. That would be more for an advanced computational methods class. We'll be using some special matrices and some special terminologies that will imply differences in how we solve the system of equations. One is we can talk about a symmetric matrix. So in a symmetric matrix, what we do is we look for symmetry of the elements about the diagonal. So we have a diagonal here, and notice there's 2's in these two positions. There's 9's in these two positions, and then 5's, and then 4's in these opposite positions, and then 2 8's and 2 0's. So if we were to flop that matrix or spin that matrix around the diagonal, we would end up with the same matrix again. So we call that symmetric. If we have what is called a diagonal matrix, that means there's just numbers going down the diagonal. Everywhere else is just all zeros. And when we start solving differential equations with finite difference method, these diagonal matrices will come up at that point. If we have a diagonal matrix, but all of the numbers going down the diagonal are ones, we call that the identity matrix. This is as close to the number 1 as a matrix can get. If we multiply any matrix by the identity matrix, we just get that matrix back again. Well, it makes sense if we have something equivalent to the number 1, a 0 matrix is the equivalent to 0. If we multiply any matrix by the 0 matrix, we get the 0 matrix. We have what are called triangular matrices. In this case, we have an upper triangular matrix. And remember when we were solving that system of linear algebraic equations, I pointed to the setup of coefficients on the left, how it formed a triangle. This is what it would look like if we cast that system of equations into matrix form. So anytime we see triangular matrices, we immediately think to ourselves, this is a set of equations that is almost solved, and all we really have to do is this very fast backward substitution step. Likewise, we can get a lower triangular matrix, and we think of this as the same way. It's an almost solved matrix. We can have what's called a banded matrix. It's a bit like a diagonal matrix, but there's numbers running along more of the diagonals, but not all of the diagonals. And if we look at the span over which we have diagonals, non-zero diagonals, we refer to this as the bandwidth of the matrix. So banded matrices will come up all the time in physics and science. Anytime we solve a system of equations using finite differences or finite elements, we'll get banded matrices. There's also what's called a Vandermonde matrix, and we'll run across these when we fit data to polynomials. And I guess one thing that I wanted to point out here is when they get very large, they become ill-conditioned. And this ill-conditioned word is something we'll talk about next that has to do with the health of a matrix. Some matrices are just better than others. And so when these Vandermonde matrices get very large, there can be some problems. And we don't have to worry about it in this course. We won't be solving very large matrices, but there's very well-known fixes to all of that. Block matrices. We can think of these as matrices of matrices. So right here I'm showing a 2 by 2 matrix. However, each of those elements of the 2 by 2 matrix is also itself a 2 by 2 matrix. So if we put all of this together, we can see that we have a 4 by 4 matrix. But thinking in terms of block matrices, it lets us calculate and construct these little matrices that are probably easier to construct, and then from that construct bigger and probably uglier matrices. And we'll definitely make use of this later in the semester. Sparse matrices. Sparse matrices is when your matrix contains almost all zeros. So I'm showing something here that contains mostly zeros. There's a few ones in here. But in fact, as your matrix size gets larger, it's very common to have a matrix that's 100,000 by 100,000 elements. And maybe there's only numbers going down 3 of the diagonals. So most of the time when we're solving differential equations, our matrices are 99.999% all zeros. It does not make sense to store those zeros as double floating point precision numbers. That takes up a lot of memory. So what a sparse matrix is, it's still a matrix, but what we do is only store the non-zero elements. So in a way, we have more information to store. We not only have the numbers, but we have where they go in the matrix. So if you have a full matrix or a matrix that just has a lot of numbers and you store it as sparse, it could actually end up taking more memory. But most of the time, your matrices are 99.9% sparse. And there is lots of literature out there on algorithms that are optimized for sparse matrices. If you're using MATLAB, you're in luck. All you have to do is tell MATLAB that a matrix is sparse, and then you can forget about it. MATLAB does everything else for you. But rest assured, there is lots and lots of literature for very optimized algorithms dealing with sparse matrices. Another way that I like to think about a, a matrix equation is just in terms of its size. And just by looking at it, we can see a lot about it. So here we're looking at a matrix equation. We see there's just as many rows as there are columns. This means we have just as many equations as there are unknowns. That means we can solve this with very well-established algorithms. We're for solving node analysis or loop analysis and circuit theory, or solving differential equations, or fitting to polynomials. We end up with a square matrix that's very easy to solve. And this really is what we were talking about before when we were solving just that standard set of algebraic equations. We were solving something that had just as many equations as it has unknowns. So this comes up most of the time in linear algebra. There's also times where we will have more equations than we have unknowns. So we have more rows than we have columns. This happens in curve fitting. You may have a whole bunch of samples of data and you want to fit those to a line or a Gaussian or something like that. And this is not solvable by the standard algorithms that we talked about with the square matrices. And there actually is no exact solution here, and we solve this type of set of equations as a best fit. The most common is solving this in the sense of least squares, and this is something we will do when we get to curve fitting. Well, there's the other situation where we have more unknowns than we have equations. So we don't even have enough information to solve our problem. This happens in optimization, and we will definitely get to that before the end of the semester. Now let's talk about the health of a matrix. All matrices are not the same. So let's look at this system of equations, which we've also cast into matrix form, and let's ask the question, is this a solvable system of equations? So go ahead and pause the video and give this some thought, and then hit play again, and we'll say the answer and talk about it. This is not a solvable system of equations. That's because the first equation and the second equation are the same equation. So effectively, we really only have two equations here. That first or the second equation is not providing new information. To solve this, we need three equations that are all providing new information. Let's look at this system of equations. Is this system of equations solvable? So go ahead and pause the video and come back, and you'll get the answer. This is not a solvable system of equations. Notice that the second equation is just 2 times the first equation. So really, that second equation is not providing new information. So this system of equations is not solvable. We would not call this square matrix on the left a healthy matrix. It is not solvable. Okay, what about this system of equations? Is this solvable? Go ahead and pause the video and think about this. This is also not solvable, although maybe this is harder to figure out why not. But in this case, the second equation is simply the sum of the first and the third equations. Now that's hard to see. Maybe I would have caught that, or maybe not. But the point is, since the second equation is the sum of the first and the third, again, our second equation is not providing new information to this. And so it's not solvable, and that matrix is not a healthy matrix. Is this system of equations solvable? Go ahead and pause the video and think about it. This is not solvable. Notice we have a column entirely of zeros. So that's not providing any information about how y is affecting things here. So we can't have any columns that are all zeros. So there's a lot of things to look for, and when we start talking about different combinations of multiple equations, that gets really, really hard to tell. And so it will be really nice if there is a test, and there is a nice simple test to see if a system of equations is solvable. But in general, all of the rows have to provide new information. This means they all have to be linearly independent. We can't have any rows that are all zeros. That's just a zero equation, doesn't provide any new information. No columns can be all zeros. So what is the one simple test that we can do? Well, AX equals B is solvable if the determinant of the A matrix is not equal to 0. If the determinant is 0, that means we violated one of these rules and it's not solvable. Now, we could be solving by best fit and optimization and other techniques, but it's not directly solvable. So what about this system of equations? Is this solvable? In this case, notice the first and second equations are essentially the same, except one of the one coefficient in front of the x is now a 1.0001, and on the right hand side, instead of an 8, it's an 8.0001. So the first and second equations are different, but not very different. So what does this mean? Well, we would call this ill-conditioned, and it's this idea that a matrix can be more or less solvable, that it's not necessarily a binary thing. Some systems of equations are just better conditioned than others. This would not be well conditioned because the first and second rows are almost the same, just a very, very small difference. And when we have a situation like this, we expect our matrix equation to be very touchy. We will change our coefficients maybe just a little tiny bit, and the answer might change a lot. And that's a rather unstable, touchy sort of thing. And if we were to solve that with an iterative algorithm, for example, that iterative algorithm may never converge or be very, very slow. So this is lumped into something called the condition number of a matrix. We won't deal with this a whole lot in this course. I consider this a more advanced topic, but we'll mention it. And it's really the ratio of the smallest to largest singular value. I think I said that backwards. The ratio of the largest to the smallest singular value. Don't worry too much about the math of how this is constructed. Just understand that there's this thing called a condition number. And in MATLAB, you can just type in COND and then put your matrix in parentheses and calculate what the condition number is. And it's a measure of how touchy the matrix is. The bigger the number, the more touchy it is, the more ill-conditioned it is. Let's go through some examples to give you a feel of condition numbers. And we'll use matrices that we discussed before. I believe this was our first matrix that we figured out was not solvable because the first and second rows were the same. So what is the condition number of this? It turns out it's something 10 to the 16. That's essentially infinity to the numerical precision of the computer. So that's a really, really high condition number. Something is seriously wrong with this matrix, and we can see it. It's obvious to see in this case. The first and second rows are the same and not contributing new information. Okay, what about this equation or this matrix? That's a fine matrix. So each equation provides new and unique information, and the condition number was in the range of 7 to 8. What about this one? This matrix is the first matrix, just with one of the elements changed by a little tiny bit. Condition number in this case is 10 to the 5. Again, we can look at that condition number and say that something's horrible about it. There's something really bad. And looking at the A matrix, we can tell this intuitively now, but if the different rows end up being integer combinations of others and there's maybe some multiple small changes, it can get very, very difficult to see the conditioning. But the condition number will tell you all of that information. Same thing now. I just made the change in that one element a little bit smaller, so it should be better conditioned. And it is. It's 10 to the 3. This is probably very solvable. On to matrix operations. I think we can move pretty fast here because this should be mostly review. Addition, when we're adding two matrices, we add them element by element. So for the very upper left element, we'll take A11, add it to B11, and that gives us the upper element in our new matrix. So each element we add. It's an element by element addition. It makes sense to be the same thing for subtraction. We are doing an element by element subtraction. Very easy. Multiplication by a scalar. We just bring that scalar into the matrix and multiply every single element in that matrix by that scalar. Multiplying two matrices to get together. Hopefully this is review, but we do this weird row column thing. So to get the very upper left element, the 1, 1 element in this matrix, we will take the first row in A and multiply it element by element with the first column in B. So it's A11 times B11, A12 times B21, A13 times B31, and we get this element. And we work our way through the matrix doing these row column operations and eventually get our answer. So I could talk a lot more about this, but I really hope this is review. If it's not, please go to Google, search for matrix multiplication, and know that very well. It's not hard, but you need to know it. The one thing I do want to point out before we move on, that matrix multiplication is not an element by element multiplication. In other words, the element here, the 1, 1 element in our answer, is not just A11 times B11. It's more complicated than that. We're doing row column operations. Matrix transpose. Here's an animation on the right where we're flipping the matrix about its diagonal. And when we do that, we get the transpose. And a real compact way of writing that is Aij in our new matrix, our transpose matrix, is Aji in the original matrix. And I even color-coded the blues here. It's these upper and lower triangles that essentially invert around each other. And the way to visualize it, I've animated. So I'll let this run for another second or two, but watch that. And to keep the orientation in mind, I also added those little colored circles. Very similar to a matrix transpose is what's called a Hermitian transpose, sometimes just called the Hermitian, sometimes called the complex transpose, but it is a transpose operation followed by a complex conjugate of every single number in the matrix. Very often when we are solving differential equations and we have complex numbers, when we want to do a transpose, it really needs to be a Hermitian transpose in that case. Determinants. What is a determinant? Boy, it's very difficult to express the physical meaning of a determinant because it depends on the physics of what built the matrix to begin with. But if we were to try to give an intuitive feel of what this is, we can think of the determinant as sort of a magnitude or a volume of the matrix. But it comes up a lot in linear algebra. We've already seen it as a way to tell if a system of equations is solvable. We have matrix inverses, and we'll learn later how to calculate matrix inverses. But if we, for example, have the inverse of the A matrix and multiply that by the A matrix, we'll get the identity matrix. Remember, the identity matrix is the matrix version of the number 1. So matrix inverses come up all the time when we're solving systems of equations, and so the ability to calculate the inverses is very important. Matrix division. This is a source of confusion. So let's look at these two equations. In both cases, we are dividing by A. However, in the first equation, we are pre-dividing by A. And in the second equation, we are post-dividing by A. And these give two different answers. We are not allowed to reverse the order of this. We have to retain that order. So in MATLAB, we can actually use both of the slashes to distinguish what's happening here. If we use the backward slash, it's A inverse times B. And if we do the forward slash, that's B times A inverse. Now there's also something very special here. It looks as if we might calculate the inverse of A and then either pre-multiply or pre-divide. And it turns out that's not the case. When we see systems of equations like this, we do not calculate the inverse of A. That would be a very, very slow process. Instead, there's very optimized and efficient algorithms for doing the matrix division, which never actually explicitly gives you the inverse of A, and so it's much faster. In fact, I would say in linear algebra, it's quite rare that we actually calculate the inverse of matrices. Normally, we're just backward dividing two different matrices, and we never explicitly need the inverse. So if you're ever typing computer code and calculating the inverse of a matrix, really ask yourself, should I be calculating this matrix inverse? Because if you do, it's much, much slower than ordinary matrix division. So something to be cautious of. Matrix multiplication, a very similar thing. We can pre-multiply or post-multiply, and these are not the same. A times B does not equal B times A. We're not free to reverse that order. Now, sometimes we can. For example, when both A and B are diagonal matrices, when each only has numbers going down their center diagonal, in that case, we actually are free to reverse the order. But in general, we are not free to reverse the order. I could also say the same thing for division. If both A and B are diagonal, we are free to reverse that order. But in general, we're not. When we are manipulating matrix equations, we can treat the matrices as variables, but they follow a slightly different form of algebra laws. The commutative laws, we can reverse the order of additions. That's not a problem. That's just element by element. But when it comes to multiplication, because we're doing these row-column operations, we are not free to reverse that order of multiplication, except in the one case where both of the matrices are diagonal. There might be other special cases where maybe you get lucky and this works, but in general, do not reverse the order of multiplication. The associative laws. Once we write a chain of additions or products, as long as we keep the matrices themselves in the same order, we can change the order that we're doing the multiplication. So for example, in the multiplication, we have A times B times C. We can choose to first multiply A times B and then multiply that product by C, or we can multiply B times C, but then we have to pre-multiply A times that product we just calculated. So as long as we're keeping the matrices themselves in the same order, we can do the math in whatever order we want. The distributive laws, this works exactly like distributive laws for regular algebra, but we need to be very careful about the order that we're keeping the order. For example, if we have the sum of two matrices multiplying a third matrix, we can distribute this out, but we have to keep C post multiplying both A and B. Likewise, if we have a matrix pre-multiplying a sum, we are free to bring the A in here, but the A has to pre-multiply both B and C. And we can talk about a bunch of different properties of matrix inverses. If we divide a matrix by itself in any way, we get the identity matrix. If this doesn't happen, then we probably didn't have the inverse of the matrix correct to begin with. The inverse of a matrix is that matrix itself. Now here's a strange one. If we have the product of two matrices and we invert the product, we can write this as the inverse of the two matrices multiplying each other, but we're reversing the order. The inverse of the transpose is the same thing as the transpose of the inverse, so we can actually reverse the order of the operation. The transpose of a transpose is the matrix again. We can take the transpose of the sum of two matrices, and that's simply the transpose of each individual matrix added together. And then a bit like this law with inverses, where when we inverted the product of two matrices, we had to reverse their order. Same thing with the transpose. If we're multiplying two matrices and we take its transpose, we write that as the individual transposes, but multiplied and in a reverse order than they were over here. So that's an easy one to miss, not reversing the order. Addition with a scalar. If we have a scalar number added to a matrix, that really doesn't make sense. If we forced it in some languages, I believe if we do this in MATLAB, it adds that scalar to every single element. But really, that should not make sense. We need to do math with things that are of compatible size. So really, if we were to add a scalar to the matrix, probably what we meant to say is this scalar times the identity matrix. In other words, this will give us a matrix with alphas running down the diagonal, and that we can add to the matrix A. And so we're adding alphas down the diagonal. Multiplication with a scalar. Well, we sort of have a distributive law here. We can take this alpha and bring it in. And once it's a scalar, it doesn't really make sense to think about post or pre-multiplication or division. We can just associate the scalar with each one on either side. Typically, we'll write the scalar to the left, but that's just convention. And then if we're multiplying a scalar by a product, we can associate that scalar with either one of the matrices. That doesn't matter. And last, some special operations with operations with special matrices. If we multiply any matrix by the zero matrix, whether that is a pre-multiply or post-multiply, we get 0. Any matrix times the identity matrix is just that matrix back again. And of course, if we add the 0 matrix to any matrix, we just get that matrix back. And if we subtract 2 matrices, we get the 0 matrix. Let's practice some of these matrix algebra rules with an example. Let's say we want to simplify the following expression. And notice I'm using the notation with bold letters instead of the square bracket letters. Not a big deal. So how do we simplify this? Well, first, I might recognize that there's a d added to both sides. So what I'll do is subtract d from both sides. So then on both sides, I have a d minus d, which we know is the 0 matrix. So we have the 0 matrix on both sides. Well, the 0 matrix added to any other matrix is just that matrix again. So we can just drop the zeros from the matrix equation and end up here. So what's next? Well, what I did was invert both sides. So on the left, we already have an inverse. So the inverse of the inverse is just this expression here. So we just have C inverse times A. But we have the inverse of BC now. Remember how we do that? We reverse the order of B and C, so we have C times B, but then we invert them individually. Okay, what's next? Well, I'll recognize that we are pre-dividing both sides of this equation by C. So what I can do is pre-multiply both sides of this equation by C. And now I have a C times C inverse on both sides, and this is the identity matrix. So we have an identity matrix on both sides, but the identity matrix times any other matrix is just that matrix. And so we simplified this first matrix equation just down to A equals B inverse. Very quickly, I want to go through some common linear algebra problems and come up with some general conclusions. Very often, we will get an AX equals B. This happens in physics and engineering when we have a problem that has some kind of excitation and there's only one answer. So maybe we're solving a circuit theory problem trying to calculate the voltage across a resistor or something like that. And so we have power sources, and those power sources end up being lumped into the B here. But the point is there is one specific answer to this. So here's an example of how we end up with AX equals B solving a differential equation. This is something we're doing later in the semester. So we start off with a differential equation that we want to solve. And in this case, F is our unknown and B is an excitation of some sort. What we'll do is approximate those derivatives with finite differences. That lets us write that finite difference equation as a set of linear algebraic equations. And the process going from the differential equation, that set of equations. That's something we'll cover in detail later. But suffice to say, now we have a huge set of linear algebraic equations. Well, we can put those into matrix form, and there is our AX equals B form. And we solve that using a backward division. And once we have the answer, we process F and learn something, hopefully. But the point is, it had an excitation and only one answer. Another thing that can arise is something called an eigenvalue problem. The most common is the standard eigenvalue problem, but there's also a generalized eigenvalue problem. Think of this as a test. We have some differential equation and we're asking the question, what could happen? So we're asking for possibilities here, not one specific answer. So we make a guess. So if we have this big ugly matrix, we pre-multiply x, and if in doing that we get the exact same answer back, just scaled by a constant, that's a valid answer. But we're asking about possibilities, and it turns out there is always an infinite number of eigenvalues and eigenvectors or solutions to an eigenvalue problem. However, because we're solving these numerically, our matrix A is only so large, we'll only be able to resolve that many answers. We'd have to add more numbers, more rows and columns to A to get more answers. So think of this as asking a question, how can a guitar string resonate? Well, it can resonate where the whole string is just going up and down in an arc. Or it could resonate as a second order mode where the left half and the right half are going up and down in opposite proportion. And then there's the third and fourth and fifth mode, and there's an infinite number of ways that a guitar string can resonate. If we just keep going to a higher and higher frequency, we can come up with more of these complicated modes. So eigenvalue problems are just asking for possibilities. And so there's multiple correct answers and no source, no excitation for an eigenvalue problem. Determinants. Talked a little bit about this. We think of this as sort of a magnitude or volume of a matrix, but really the physical meaning can come once you know the physics of what built your matrix A, what built the matrix equation. So the determinant of a 2 by 2 matrix is simply the product of these two elements minus the product of those two elements. That's our determinant. And we can go to larger matrices. So for example, a determinant of a 3 by 3 matrix, what we'll do is we'll pick a row. We'll pick the top row and we'll say this is A11 times the determinant of this matrix minus A12 times the determinant of a 2 by 2 matrix composed of this column and this column. And then plus A13 times the determinant of this matrix. And we could go on to larger matrices, and we walk across a row, we'll have elements times a 3 by 3 matrix, and then walk across those, and it's a hugely complicated thing to do by hand for large matrices, but the computer can do this very fast and efficient. And last is Cramer's rule. This is an easy way by hand for solving a set of linear algebraic equations. No real need to go through that here. This is even discussed in high school many times. So that's it. I hope this lecture is useful to you.